Hello everybody, my name is Yan Song and from the Technical University of Munich. I'm very happy to be here to present our work, Learning Dynamic Robot-to-Robot Handover. Object handover is an essential ability for robot manipulation. Most of the previous work focused on human-to-robot or robot-to-human handover and separate the handover into a pre-handover phase and a physical exchange phase. For current robot handover, during physical exchange period, the giver and the receiver's arm keep still. After the object is fully grasped by the receiver, then the giver begins to release the object. The whole motion of the handover looks weird because the hand and the arm's motion are fully decoupled. In contrast, when human performs a handover, the object is transferred in a dynamic manner, which means both the giver and the receiver are allowed to have a certain speed during the physical exchange. And some collision may also occur in this process. By comparing the human and the robot's behavior, we consider that how to enable the robot to make a handover in a dynamic manner will become the key point to achieve a human-level performance. For dynamic handover, in the physical exchange period, the giver's motion, receiver's motion, and the object itself can be dynamic. To achieve this, we design a parameter-based robot handover skill. In our skill, the desired motion of the robot arm is modeled with dynamic movement primitive. In addition, there are three time-related parameters, namely speed factor, which modifies the speed of the whole trajectory, the giver's releasing time, and the receiver's grasping time. By tuning these time-related parameters and changing the goal of the DMP, we can adjust the time of the physical exchange and the corresponding giver's and receiver's state. Considering the possible collision in this process, the robot is controlled with variable impedance controller, and the stiffness profile is represented with local weighted regression. As for the learning algorithm, we use the path integral policy improvement with covariance matrix adaptation to search for the optimal parameters. To approve the feasibility of our proposed method, we make two groups of experiment with different strategy. And in our first strategy, we focus on a stable handover. The giver can only release the object after it is fully grasped by the receiver. And in our second strategy, we don't set any constraint and let the robot to learn it freely. The initial distribution of our evolutionary algorithm is obtained from human demonstration. In the demonstration, the whole motion looks slow and unnatural. And then we use the accelerated demonstration as our comparing baseline. With the accelerated motion, the whole process becomes faster. However, the uncoupled issue of the robot's arm and hands motion is still there, which makes the handover look weird and unnatural. Comparing to this, in the result of the skill based on our first strategy, we can already feel a better cooperation between the motion of the hands and the arms. And in our second strategy, the robot can freely explore the environment without any time constraint on the hand motion. As a result, the robot can transfer the object in a dynamic manner, and the whole process looks quite similar and natural. From the result shown in the diagram, we can see that our proposed strategy can greatly improve the efficiency of the handover under the premise of controlling the impact force during the interaction. This is our presentation. Thank you for listening.